Welcome to this course on nonlinear systems. I am Boubacar Boukhzar and I am Professor of Electrical Engineering. In this first chapter, we'll take a global overview on nonlinear systems. So, as you know, as an engineer, you have to model systems for many reasons. You can evaluate their performances. You can also analyze their behavior to see if they are stable and unstable. You can use this model to simulate the system. You can also use the model for a controller design. However, in real world, all systems are nonlinear, distributed parameters, and very complex. We'll see the signification of the first 2 points, nonlinearity and distributed parameters. At the end, we get very heavy models that are useless for controller design. For persons that had get a course on linear system control, you only use simple models like state space representations or transfer functions for controller design. So the solution is to make some assumptions that practical consideration justify to get an acceptable complexity model. So after modeling, the automatic control engineer need to analyze the model and also define requirements for the controller and then design a controller to meet these requirements. We have 2 ways to do this. First, assume that the system we want to control is linear around a given operating point. We call this point a steady state or an operating point. For this, we compute a linearized model around this point. The other solution that we will discuss in this course is to use directly the nonlinear model, and we will get a nonlinear controller using nonlinear control design techniques. Both approach has its advantages and drawbacks. Starting by linear controllers, the advantage is that the linear models are simple and that there is a large choice of control design techniques and control structures. So the control structures are the kind of controller, and the control design technique is the technique we use to tune these controllers. For example, we can use classical PIDs, lead lag compensators, pole placement in both transfer function and state space approach. We can use both Nyquist and Black charts to design these controllers. We can also use the state space approach, design linear quadratic or linear quadratic Gaussian using Kalman filter. The person that get a course on linear systems know this concept. An interesting approach also for linear controller is the robust linear control theory. We can use concepts like mu analysis, mu synthesis, and H to H infinity design. All these controllers are simple to be implemented either in analog or digital way. For example, you can implement the integral or derivative action using operational amplifiers and passive components like resistors and capacitance. This should have been seen in a basic analog electronic course. However, these controllers are limited and their performance decreases as far as we get away from the operating point. And also, linear control theory cannot explain some phenomena like limit cycles or chaotic behavior. We will see all these phenomena in the next chapters of this course. The other approach is to directly use the nonlinear model and to design a nonlinear controller. The advantages are that the nonlinearity are directly considered. No assumptions are made about the operating area. So the operating area is large and include all the operating conditions of the system. We get better performance as we have no limitation. However, these controllers are more complex, more difficult to implement, and consequently more expensive. We'll recall some concept about systems representations. So what's a system, what's a physical system, and what a process? We call a system or a physical system that we want to control a process. Generally, physical systems are complex ones composed of a set of interconnected elements that achieves a certain goal. For example, we have mechanical or electromechanical or mechatronic systems like a car, an aeroplane. We have also biological systems like a cell that is a very complex system. So if we want to study in automatic control point of view one of these systems, we have to focus only on one aspect of the system. The second concept is the concept of dynamical system. Here we talk about the model of the system. Dynamical system is a mathematical concept. It's a mathematical model of the physical system. It consists generally of a set of ordinary or partial derivative equations that link the system variables. These equations are also called evolution equations. From the input-output point of view, the system can be seen as an operator. This operator transforms functions that we call input functions or input signals to output that we call output functions or output signals. So be careful, here we deal with functions, not with values. We will give here a possible system classification to see where nonlinear systems are situated. To make any classification, we have to define a criterion or a property. Dynamical systems are systems that are described by differential equations. We have two kinds of differential equations. Distributed parameter systems that are described by partial derivative equations like the heat equation or the Navier-Stokes equation in fluid dynamics. And we have lumped or localized parameter systems. In this case, the system is described by ordinary differential equations. We will not have here partial derivatives. So in this case, we can have a nonlinear or linear case. In the nonlinear case, the system is described by a nonlinear differential equation. Two special cases: the input-affine nonlinear system, where the system differential equation is affine regarding the input, and the other case where they are not. Linear systems are a set of linear differential equations. We will see what's a linear differential equation. It will be just a linear combination of the system variable derivatives. And the more general case is the linear parameter varying systems, where the parameters of the differential equation are variable in time. The second case is the linear time varying system. Here the coefficients of the differential equation are known function of time. In the more general case, the coefficients depends on parameters, but we generally doesn't know the temporal expression of these coefficients. And the most common case, the case that you have probably seen in basic control theory courses, the linear time invariant systems that are described by linear ordinary differential equations with constant coefficients. We'll also recall the concept of a deterministic system. A deterministic system is a system that gives only one possible output for one only given input. It's described by a deterministic differential equation. So we have no statistics or probability or stochastic process here. The other case is the theory of stochastic systems that we in this case we consider the input and the output as stochastic signals. We can also consider the system equations as stochastic in the case if they have coefficients that are probabilistic variables. A causal system is a physical system that doesn't give input if we don't give him it doesn't give output if we doesn't give him input. So the answer at time t depends only on the input starting from t, so the output and going back until t, sorry. So we have here the tau that depends on t, so the output doesn't depend on the future. Stationary time invariant system has parameters that are constant and doesn't vary in time. So if we delay the input, the output will be the same and delayed by the same amount.